So today, man, let me show the dog again real quick. Okay, so this is my dog. She got shaved, so she looks a little weird. But she helped me develop these slides. The slides are about infrastructure and tooling for deep learning. And I want to start off by describing the dream that practitioners have, which is that we provide data and then we somehow just get a really good machine learning prediction system, and it's available as a scalable API or an edge deployment. And that deployment generates more data for us, which we can use to improve our system. And that's really the dream. The reality is that you don't just grant data to the system. You have to find it, aggregate it, process it, clean it, label it, version it. Then you have to write and debug model code. Then you have to somehow find compute, run a lot of experiments, review their results, discover that you did something wrong, or maybe just try a different architecture. So you write more code, provision more compute, do it again. At some point you're happy with it, so you deploy your model. And then you have to monitor the predictions that the model makes on production data such that you can gather some good examples, aggregate them, process them, clean them, label them, add them to the dataset version, and then do it all over again. I'm not the only one who's saying, what the dream is. This is Andrej Karpathy's slide from a couple of years ago, I guess, called Operation Vacation. So that Tesla self-driving, their dream, right, is to build a system that basically goes from the data they've gathered through their training, evaluation, and inference processes, deployed on the cars, and then as people drive, gather more data, and then just seamlessly add it back to their data set, and then do the process again so that they can all go on vacation and see a model improve even in their absence. And when you think about what the dream takes, it's actually not mostly machine learning code, right? It's all the stuff around it to create the system for this machine learning system to improve. And this observation was made a few years ago, most famously in this paper called Machine Learning, the High Interest Credit Card of Technical Debt. The observation basically is that the machine learning part of the code base is actually a very small part of it. And in trying to deliver that part of it, you take on a lot of debt in building up all these other components of the system that then have to be maintained and invested in and so on, just for your little thing that you originally set out to do to be able to do its thing. We can break down the landscape of all this infrastructure that's necessary into three broad buckets. One has to do with data. The other has to do with the training and evaluation of the models. And then the third one has to do with deployment. In data, we have the sources of the data, logs, databases, file system, images and stuff like that. Data lakes and data warehouses like Databricks, Snowflake, BigQuery, Redshift. Processing of the data via Airflow or Apache Spark or Dagster, stuff like that. Exploring the data with pandas, potentially transforming it into forms that are more amenable to exploration with SQL, with dbt. Versioning some final kind of data artifact. And for a lot of the data that we deal with, we also have to actually label it because it comes in a way that's not immediately useful for training. On the training side, we have the source of compute, could be hardware, could be cloud providers, of which there are a number of different vendors. Then once you've provisioned the compute, you have to manage the resources that you now have in order to efficiently use them. There's basic software engineering skills, of course, that play a role in all of this. There's deep learning specific and machine learning specific frameworks, which allow you to do distributed training more easily also. All this training is generating a lot of data that you need to manage. So there's things like TensorBoard, weights and biases for experiment management. And running experiments blind is one thing, but it'd be nice if we could be guided in like what experiments to actually run. This is often called hyperparameter tuning, and there's other solutions for that. Once we have a model we're happy with, we want to be able to reproduce our results and ideally just automate the process. So that's continuous integration. We want to ensure that the model performs as well as we expect via testing. If we're deploying on mobile or hardware, like robotic hardware or some kind of sensors or anything like that, often called edge computing, we need specialized tools to do that well. If we're deploying to the web, there's different deployment options available to us. We will want to monitor our running model in order to catch certain problems with it and also maybe find good data points to add back to our data set. Around all of this, I broke it into 3 buckets, but in fact, you can think of it as one kind of ML ops process. And there's a number of vendors offering like an all-in-one ML ops solution, like Amazon SageMaker, Domino Data Lab. And then most recently, also there's this concept of a feature store, which plays a role in data, but also in deployment. So I put it in the deployment bucket. And today we're going to talk about the middle part of this diagram, so training and evaluation. So I'd like to start with the most foundational thing here, which is just software engineering skills. The programming language we use for machine learning and definitely deep learning is Python. And the reason for that is actually because of the libraries, not necessarily because of properties of the language, but because of the libraries that have built up over time. Python's the clear winner in scientific and data computing. There are some nice things about it. It's very interoperable with low-level languages like C, but that's also kind of a negative. It'd be nice to just not have to leave Python and be able to write really performant code. As things stand today, you kind of have to write the really performant scientific and data computing stuff in C using Python and then integrate it, or C++ or any other low-level language, and then integrate it with Python via a library. But it's a nice experience for writing scripts, and I think a lot of scientists and statisticians and people that aren't computer science first, but are some other discipline first, came to Python because it's such a logical language to kind of write. It almost reads as English language. And so now it's the scientific language. To edit code, we use text editors. There's old school stuff, old school options like Vim, Emacs. We can spark a little poll, maybe if someone wants to post a poll, right? Vim versus Emacs, key bindings. There's notebooks, which is an interesting way to do scientific computing, where you execute one cell at a time and see the results of running a cell, and you can execute cells out of order. Jupyter is the Python solution for notebooks. There's new school editors, of which I think the clear winner is VS Code, Visual Studio Code, open source project from Microsoft. And there's also Python-specific integrated development environments like PyCharm, which are also quite nice. Visual Studio Code makes for a very nice Python experience, and it's free, it's easy to set up, it has a powerful ecosystem. So that's what we recommend. I want to point out some nice things about it, just in case you haven't used it so far. There's built-in version control, staging, and diffing. So you can see like the diff between the branch you're on and the code that you've actually edited. And you can commit straight from your editor. You can look at the history of commits. You can do a lot of stuff without actually leaving your editor. You can peek at documentation for different functions. So as you start typing, there's powerful autocomplete that it's called IntelliSense that analyzes your code base, analyzes the code base of your dependencies, and then is able to present helpful documentation autocompletes for you. You can open projects remotely very easily, which is quite nice. So the Farm2 is a machine that I have access to, and with just one click, I'm able to get a text editor on another machine. You can lint code as you write, so you can see certain highlights, maybe problems, potential problems, syntax errors, and other problems with your code. This is another view of Visual Studio Code that I just wanted to show that you can also use the terminal in the same window, which is really the way I do things now. I used to use the terminal separately from the editor, but now I use actually the integrated terminal in the editor, and it's just super nice. And specifically for notebooks, it's quite nice because, or when you're working on a remote machine, let's say you start a notebook in the terminal, so you say Jupyter Notebook, that starts a notebook on that server. And what VS Code does is it automatically forwards the port from the remote machine to your local host. So you can open the notebook in your own browser just very seamlessly. I want to make a note about linters and type hinting. So linters are automated rules for your code. So for example, should there be a line length limit, right? Some people say, 80 character lines, that's the max. And if a line goes over that limit, then it should be broken up into multiple lines. Well, once you make that decision, right, is it 80 characters, 100 characters, whatever it is, once you make that decision, that should be codified and done automatically. You shouldn't have to worry about it. So, and that goes for a lot of things. How should variables be named, right? Camel casing versus underscore casing, snake casing. Everything that can be codified should be. And additionally, static analysis can catch some bugs. So let's say you use a variable that was never defined. You might not see that, but a static analysis program like Pyland will notice it and highlight it in red so that it's very visible to you. And then we can also, if you see here in the train model function signature, it says it expects a variable named model, and then it says, colon model. That means the type of the variable that it expects is model. Epochs, it expects an int, batch size an int, GPU index, an int that can be none, right? So an optional int. And this kind of thing both documents your code, which is very helpful, but also can catch bugs. So if you call a function with an int, but it expects a float, or vice versa, there might be some bugs there. And we'll set this up for our code base in the labs in an upcoming lab. So Jupyter Notebooks is something I'm sure you guys have seen because they've become really fundamental to data science. And I think they're great as a first draft of a project. And I think Jeremy Howard from Fast.ai is really good to learn from. Like his Fast.ai course videos, he's just a notebook wizard, flying around, doing all kinds of stuff. Very inspirational. But it is difficult to make scalable and reproducible and well-tested code bases with notebooks. And the reason for that, drawing on a blog post called 5 Reasons Why Jupyter Notebooks Suck. The reasons for why it's hard to make a good code base with notebooks is because they're hard to version. They intersperse, your actual code and the cell output. And so you either have to not commit the cell output, in which case it's a little less useful as a notebook, or commit the cell output, in which case it keeps changing, whereas your logic might not have actually changed. The development environment of the notebook is pretty primitive. It's in the browser. It works okay, but it could be a lot better. It's not VS Code. They're hard to test. There's out of order execution can lead to artifacts where it just doesn't make sense. Like the state of your notebook doesn't make sense if you read it from top to bottom, but you might have executed from bottom to top or something like that. So it's just hard to reason about the state. And then it's hard to run long or distributed tasks from a notebook interface. The counterpoint to all of that is that some companies that do good machine learning have based their ML workflows on notebooks. So there's some people committed to notebooks. And once again, Jeremy Howard from Fast.ai uses notebooks for everything, including developing his Fast.ai code base. And there's a project called NBDev from that group of people that just shows you a way to develop, good, well-tested code still in a notebook. I don't personally vibe with it, but I want everyone to know about it in case they do vibe with it. An interesting recent project that's kind of an alternative to notebooks is called Streamlit. And it fulfills this need of interactive applets. So notebooks can fulfill this need via widgets. So sometimes you can drop a little widget as a cell output. So for example, a slider. And then the slider might control the value of some variable. But it's a little bit hacky to hook that up in a notebook. Whereas in Streamlit, it's like a first-class citizen. And so the idea is that you can make interactive applets, like little apps, just by writing Python code and using the Streamlit primitives like buttons, sliders, maps, charts, and such things. And it's achieved just by decorating normal Python code. And what they're working on is making it easy to share these applets with your team or even just, worldwide on the web. That's not quite there yet, but it's an exciting direction. So check out Streamlit. And then one kind of like boring administrative thing is defining all the dependencies, right? We have PyTorch, PyTorch Lightning, pandas, all that stuff. We recommend using this project called Conda for setting up the Python and CUDA and cuDNN environments. So, I want to use Python version 3.8, CUDA version 11, but not using Conda for the actual Python requirements like PyTorch and MyPy and stuff like that. So for that, we use piptools. And the reason for that is because piptools has a really nice system for breaking up requirements into several files. So you might have production requirements, which are separate from development requirements, which are separate from your test requirements. And it's really easy to do that using piptools. And it also separates locking the exact version of a package from just saying that you want that package, right? So I want NumPy. I don't care what version of NumPy I get. I just want NumPy. But for reproducibility, I want it to be stored what exact version of NumPy I used. And so just separating that out is what piptools does really well. So check out our sample project, and this is also how we do it in the lab. So the next thing we should talk about is the compute sources. What are the compute needs for deep learning? I like to kind of break it down into a basic, early development and then scaled out training and evaluation. So when we're doing early development, we're writing code, we're debugging the model, we're looking at the results. We want to, quickly do things. It'd be nice if we could use things that we're comfortable with, like GUIs. And what it could allow us to do it is actually having GPUs in our desktop, like in a computer we have access to, or a computer we can easily SSH into. And for rapid experimentation, it'd be nice if it had more than one GPU. So it could be on-prem, could be in the cloud. For scaling out your training, we're going to want to run some kind of architecture hyperparameter search. We will want to train models that just don't really fit on only 4 GPUs. And it should be easy to launch experiments onto this, compute and review all the results that are getting generated. So here it'd be nice to have a cluster of machines. Could be on-prem, could be in the cloud. The reason this matters increasingly with each passing year is because the results that are coming out of deep learning are using more and more compute, right? So I think we had this slide in the fundamentals lecture, but it's, notable deep learning results versus time versus the petaflops that, of compute that they used. And it keeps on going up. And you can see this in the transformer models that we discussed last week. So, GPT-3 still hasn't been trained by the community, right? Only OpenAI trained it using like Microsoft Cloud and millions of dollars. We still haven't done that, but Google already came out with Google Switch Transformer, which is another couple of orders of magnitude larger than that. So it's a race to fit bigger and bigger models and crunch through more and more data. So one question we have is, do we try to get our own hardware or just go straight to the cloud? And to answer that, we should look at the GPU basics. We should look at the cloud options. We should look at the on-prem options and then try to analyze what's going on, make a recommendation. So the basics of GPUs is that basically it's an NVIDIA game, right? It's still really the only provider of good deep learning GPUs. They're not the fastest. That's actually the Google TPUs, tensor processing units, which are available on the Google Cloud Platform. But it's worth, unless you're committed to only using TPUs, which I don't think anyone is, it's worth knowing about the NVIDIA GPUs. And so there's a number of them, but we can make some sense of them. So the first thing to notice is that there's a new NVIDIA architecture every year or two. And it went from Kepler back in like 2014 when the deep learning revolution was just getting kicked off, to Pascal, to Volta, to Turing. So it increases alphabetically, and then it wrapped back to Ampere. They come out with a server version of the card first, and then like an enthusiast version, like, a retail market card, but that's still very expensive. And then a consumer card that most people are just going to be gaming on. And if you're using this for business purposes, you're supposed to just use the server cards, not the, also possible to game on cards. GPUs have different amounts of RAM. This is very important because you can only compute on data that's on the memory of the GPU. So if you can't get your data onto the GPU, you can't compute on it. The more data you can fit on the GPU, the larger your batches are, the faster your training goes. So first of all, no one does 64-bit computing in deep learning. It's for some scientific computing stuff, like predicting the weather or splitting the atom or whatever. 64-bit scientific computing is often done. For deep learning, 32 bits is what you use. You just don't need that much precision. And in fact, you actually don't even need 32 bits of precision. I guess we'll talk about that next. But starting with the Volta architecture, NVIDIA developed this technology of tensor cores, which are specifically made for deep learning operations, which are mixed precision between 32 and 16-bit. So it might be, 16-bit addition, 32-bit multiplication, or something like that. They split up the bits in a very efficient way to make these matrix operations incredibly fast. And this is really good for the type of models that are prevalent today, convolutional transformer, fully connected models. There's also 16-bit, straight up 16-bit training. And that just means that you can fit larger batches on your GPUs of the same data just because it's not as precise. It works just about as well, and it is a great speed up. So going through the architectures in sequence, we can talk about Kepler-Maxwell first real quick. It's a lot slower than the Pascal-Volta architectures, and basically you shouldn't buy it, but you will see these in the cloud offerings, K80s and P100s. In fact, the K80s, what you're likely to get if you get a collab, it's almost certainly a K80 GPU on there. And yeah, so they're cheap on the cloud because they bought many millions of them and now they're stuck with them. Then there's Pascal architectures. So the 1080 Ti is from like 2017. It's still okay, if you're buying used for cheap, especially for recurrent networks where you don't get that much of a speed up from the tensor cores. And P100 is a cloud server GPU that uses the Pascal/Volta architecture. Then you have the Volta Turing architecture, which is preferred choice, over the Kepler and Pascal because it supports the 16-bit mixed precision via the tensor cores, which makes everything faster. So the 2080 Ti is like at least 30% faster than a 1080 Ti in 32-bit, but it's twice as fast if you're using 16-bit training. And the Titan RTX is even faster than the 2080 Ti. And in the cloud, you have the V100, which is the kind of, well, it's not the ultimate anymore, but it used to be the ultimate for speed in the cloud. 16 gigs, 14, I think, million 32-bit, 14 32-bit teraflops. And then most recently, as in like just in 2020, and really the consumer versions are just coming out right now, like the 3090s and 80s and 70s, is the Ampere architecture. So they have the most tensor cores, so they have the most tensor T-flops in this table. It's like at least another third of speed up over Turing, like the 2080 Ti. Here's an older benchmark that doesn't include the 3000 series, but you can see that the V100 is fastest, and then the TPU is still a little bit faster than that. But the A100, which is the Ampere version of the V100, is like 2 times as fast as the V100 for ConvNets, and even faster than that for language models. And this is according to benchmarks by the folks at Lambda Labs, which build these machines. A great resource for all this stuff is Tim Detmers, a grad student at UW. And he has a post called Which GPUs to Get for Deep Learning. Right now, he's recommending the 3080 or the 3090 as the GPU to get because it's so much faster, maybe even twice as fast as 2080 Ti. The problem with the 3000 series is their heat production and power consumption. So you can fit 4 2080 Ti's in a reasonable desktop rig, but you can't do that with the 3000 series. It would use too much power. It literally, your household electrical socket doesn't produce enough power to power it. And then they build too much heat, so you can't really fit more than 2 into a normal desktop rig. In the cloud, you have Amazon Web Services, Google Cloud Platform, Microsoft, Azure. They're the heavyweights. They're all pretty much similar in function, what GPUs they provide and how that all looks and price. AWS tends to be more expensive than the other two. GCP is a tiny bit cheaper. It also has TPUs, which is quite nice. And then Azure, I don't know people who've really used it, but it has the same kind of GPUs at roughly the same price. There's startups that are exciting. One is CoreWeave, there's Lambda Labs. So on Amazon Web Services, here's some pricing. So you can get a K80, you can get 8 K80s. Each one has 12 gigabytes RAM. That'll be $14 per hour. You can get 8 V100s. Each of these GPUs has 16 gigs RAM. That'll be $24 per hour. You can now get a special V100 with 32 gigs RAM, not 16 gigs RAM. So this is really nice for these big language models. And that's $31 an hour. And then now the most recent GPU is the A100, and you can get 8 of those. And each one has 40 gigs RAM for $32 an hour. So this is quite wild. So there's 3 generations of GPUs they provide. And we've been doing this course for a while, and the prices really don't change. They're just kind of sticking to these prices. So in Google Cloud Platform, you also have the K80, you have the V100, you also have the P100, which is a little bit cheaper and slower, and you have the A100 in some zones because it's so new. But the real star of the show might be the TPU for you, and it might be a reason to use GCP versus AWS. So the promise of TPUs is that they're more expensive per hour, but they're also a lot faster and have a lot of memory, so you can crank through training faster. I haven't personally used them. It's kind of exciting to get a TPU in a collab. I don't know if that's ever happened to you, but good to know about. Microsoft has K80s, P100s, V100s, has similar pricing. Then there's the startups. So there's Lambda Labs Cloud, which you can get either 4 2080 Ti's basically, Pascal-based 11 gig GPUs for $1.50 an hour, which is pretty great. Or you can get an 8 GPU V100 machine for $12 an hour. So that's $12 an hour versus $24 an hour on AWS. So that's making a big difference, right? There's a startup called CoreWeave, which I think pride themselves on having the lowest prices possible. And so there you can get 8 V100s for only $4.80 an hour. It's the 4th row on this table. So yeah, each V100 has 24 gigs. or sorry, it has 32 gigs. There's 24 CPUs, and it's $4.80 an hour. So that's really good. On-prem, you have some options. You can build your own machine, which is actually pretty doable, up to 4 2080 Ti's or 2 3090s or 3080s. You can buy a pre-built machine. Lambda Labs, they do the cloud offering, but they also build machines. That's their main business. NVIDIA will sell you a machine. And then there's standard kind of server PC builders like Supermicro, Surascale. There's Bison Tech. There's a bunch of them. I built this one at some point, 4 2080 Ti's. I think it cost around $7,000. And then today with the 3090s, you'd only be able to do 2 of them. Probably be around that, $8,000. The problem is you probably can't find the 3000 series GPUs because they're all sold out. I guess NVIDIA had trouble producing them at the scale they need, and also people are using them for like Ethereum mining again. But it's kind of fun to build a PC if you haven't done it. It's painful to go beyond 4 GPUs or 2 of the 3000 series GPUs, so don't try that. And then once again, Tim Detmers is your friend. He'll help you pick the components for this machine. If you don't want to go through the trouble, which is totally reasonable, you can just buy it from Lambda Labs. I configured one last night with 2 3090s, 24 core CPU, 256 gigs RAM. And it's like 11,000. So that's probably like 20% more expensive than if you built it yourself, but it also has a warranty and, probably worth it. And it's definitely worth it if you're trying to build a server grade machine, because it's just not, we can't build them. We have to buy them. So if you want to, you can buy an 8, V100 server for around 100,000. So these prices are pretty big, right? Like 100,000, that's a lot of money. But if you compare them to the cloud, it actually starts to make sense. And so here I worked up a 4X 2080 Ti machine versus a 4X V100 cloud machine, right? So we can build a 2080 Ti machine for, let's say, $10,000. It'll actually be cheaper, but let's just say $10,000. And we can use a 4X V100 machine on AWS for $12. So then if we run the machine that we build full time, then in 5 weeks, it's equivalent to running the V100 cloud instance full time. If we don't run it full time, but we run it for like 16 hours a day, 5 days a week. So that's like, you come in, you start running experiments, you run them, but then they finish at some point while you're sleeping, and then you don't work on the weekend, then it'll take 10 weeks to pay for the machine. One way to see it is, here's someone on Reddit who built a deep learning rig for like $6,000. I don't buy his claim that, or her claim that it's half as cheap. I think it's 20% markup that Lambda Labs does, not like 100%. But still, it costs a lot to train on ImageNet on 2080 Ti's. So you save $1,200, which is the cost of a 2080 Ti, every time you run a full ImageNet training if you did it on your own build instead of using the Google Compute Engine, which I thought that's like an interesting way to think about it. But another way to use the cloud is to launch a lot of experiments at once using specifically on-demand instances, also called spot instances. So I've been giving you per hour prices. There's another way to get instances, which is spot pricing, which are called preemptible. So that means you get an instance, but at any second, it might disappear from under you. And for that risk, you get a lower price, which might be okay if you're using, you're launching a whole armada of experiments at once. So it's okay if some of them die and then get restarted later. So using the cloud, you can enable quicker experiments. And so if time is a very important variable, not just money, then that's a reason to go with the cloud, because you can't like if you only have 4 GPUs, it'll take you 24 hours to run, 16 trials if each trial takes 6 hours. But on the cloud, you can actually just finish all of them in 6 hours. But the price is still pretty steep, right? So it's, you can only run 100 such experiments before you have paid the cost of a whole machine to the cloud. So in practice, the cloud is expensive, but it's also hard to make on-prem scale past a certain point. There's DevOps things that we have to do, like provision instances, make repeatable certain tasks that are just easier to do in the cloud than to try to set it up yourself. And then if a machine dies or needs some maintenance, that's going to be a constant headache if you're responsible for managing on-prem machines. And in the cloud, you wouldn't even know about it. They just, they deal with it for you. For a hobbyist, our recommendation is to build your own PC, maybe a 4X 2080 Ti or a 2X 3080 machine. And then if you want to scale out your experimentation, you could just use the same machine, just run it overnight all the time. But you could also then go to a cheaper kind of startup cloud like Lambda or CoreWeave and then get cloud instances there. For a small company or startup, I think, let's buy a Lambda Labs machine that's sizable for every machine learning scientist that we have. And then to scale out, let's buy more shared server machines and put them in a data center, or use cloud instances like V100 instances or something. And then for a larger company, let's up that 8x GPUs per scientist, or just go straight to the cloud with fast instances, because presumably, money is less of a concern. So next up, let's talk about how do we actually manage all these GPUs and whatnot. We have maybe multiple scientists using multiple machines with multiple GPUs. They might be running different environments. And what we want them to be able to do is run many experiments, with each experiment having its proper dependencies and the resources in terms of GPUs and CPUs and RAM that it needs for the experiment. And there's a number of solutions we could do. We could kind of try to script our own solution to it. We could use Slurm, which is a well-known cluster workload manager. We could go with Docker and Kubernetes, or we could use software that's specialized for exactly this use case. So the simplest thing is just maybe hand-coded stuff, right? So what we want to do is allocate resources that aren't being used to programs that will use them. We could actually just write a simple script that does that and just checks is a GPU available? If I'm about to start using it, then lock it so that other people can't use it. And you can do that. Even better, you can use a cluster job scheduler. Often it's going to be Slurm. And so the way that basically works is you have a script that defines the resources it needs. So this script needs 1 GPU, 10 gigabytes RAM, and then specifies the dependencies it needs, and then says what commands it needs to run. So that's the last line. It says Python, mnist cnn.py. And then you submit that job definition using the Slurm kind of queue runner. And so you submit it to the queue, and then Slurm executes it on a machine that has the necessary resources. And so then all of your scientists can, if everyone agrees to use Slurm, they define their jobs using it, and then the cluster scheduler correctly allocates resources to them. If that's a little too old school for you, you can use Docker and Kubernetes. So Docker is a way to package up an entire dependency stack so that, CUDA version, certain binaries, Python version, everything you need, but exclude the operating system. So a virtual machine includes the operating system in its packaging. Docker does not. It only includes the precise dependencies on top of the operating system and then the code. We'll talk more about it in the deployment lecture, and we'll use it in that lecture lab. And then Kubernetes is a way to run a lot of Docker containers on top of a cluster. So Kubeflow specifically is an open source project that's been gathering steam originally from Google, but now it's a community project that lets you spawn and get Jupyter notebooks and have multi-step ML workflows, which can include GPUs. And there's like plugins that people have that make certain things easier. It's still kind of a pain to set up. And this is actually an active area. Like, it should be a lot easier to provision compute resources for deep learning. There's all-in-one solutions that we're going to talk about, like SageMaker, Paperspace Gradient, Determined AI, that also, provision resources for you really nicely. So we'll talk about that later. Also, some recent startups have this specific thing as their main goal. So for example, there's Anyscale, which came out of Berkeley, Rise Lab. They had an open source project called Ray, which we'll also talk about. And now it's a company called Anyscale. And that's kind of their vision, right? It's like, it should be really easy to provision the compute you need, get something to work on your laptop, and then effortlessly scale it to the cloud. And then from the makers of PyTorch Lightning, there's a startup called Grid.ai, which has that same vision too, right? So it should be on your local machine, you say Python, model.py, learning rate, 1 to the power -6. Can it be as easy as typing that? We just type, grid train, say how many GPUs we want, still model.py, that's our code. And then learning rate, we can actually run a hyperparameter search, right? Just that easily. So that's the vision. We'll see if it bears fruit. But for now, the recommendation is probably to use Slurm. Let's talk about frameworks and how they can make distributed training easy. So deep learning frameworks have existed for a while, like over a decade, with Theano and Torch, really old projects actually. And you can think of where each framework might fall on this chart, where the axes are. Is it good for production use, aka is it really fast? And the other axis is it good for development, as in, is it easy to write deep learning models in this framework? And when TensorFlow came out in 2015, it was billed as really good for production. It makes the static optimized graph that can be deployed to GPUs, CPUs, even mobile devices. But the user experience of it wasn't very good, because you had to basically do this meta thinking, where it's like you would use a programming language to describe the execution graph of the deep learning model, and it just didn't really fit in how people thought naturally. Keras made it a lot easier to use. It's not a TensorFlow only project, but it is now part of TensorFlow. It's just a lot nicer of a way to define deep learning models, and kind of hides a lot of the complexity of TensorFlow behind the nice user interface. PyTorch came out a couple of years later with kind of a different pitch, right? It wasn't supposed to be the fastest model produced out of doing it in PyTorch, but it was basically straight Python. And you guys have seen that in the lab, right? So it's a really good development experience. So these are still the two leading options, TensorFlow and Keras or PyTorch, and you should use one of them unless you have a good reason not to. And both have since converged to the same point, which is TensorFlow got eager execution. And so TensorFlow 2.0, you can write code that looks a lot like PyTorch. And then PyTorch got a lot better at being fast, because this project called Cafe2 got folded into it via Torch script. So you can compile your model down to a really fast artifact. Most new projects today use PyTorch, I think because of just it's way more dev friendly for Python users. There's some libraries that have come out since that make it even better for development. So Fast.ai is a good library. It builds on top of PyTorch, and it builds in a lot of good practices, best practices. And then PyTorch Lightning is what we use in labs. Similar vein, right? Adds a very powerful training loop, encodes best practices, makes distributed training really easy. So here's some evidence that PyTorch dominates new development. At least when you look at academic publications, I don't have more recent data than this, but it's up, upward of 80% of submissions are in PyTorch. You can search for, or you can see how users are searching for PyTorch or TensorFlow. Looks like they're about equally popular right now. And, you know, why do we need TensorFlow or PyTorch? Deep learning is actually like not a lot of code if you have a good matrix math library like NumPy. So we were able to code, you know, at least the linear layer in like 20 lines of code. But we had to code our own backwards loop or backwards pass. So we had to like do a manual derivative. And yeah, if you're able to do that, then it's not a lot of code. But we don't want to have to do that. We want auto differentiation, which means we just write the forward pass. And then we want the framework to figure out how to back propagate through it. So how to differentiate the function that you wrote. And also we use NumPy, but that doesn't actually use GPU. So if we want things to run on CUDA, that's going to be a lot of work because now you have to write actual CUDA code. Also, there's like all the layer types, all the different convolutions and transpose convolutions and like LSTMs and whatnot, optimizers, interfaces to different data formats. So all that stuff really built up. So that's why we need frameworks. Except sometimes you really don't need all that stuff. You just need auto differentiation and the ability to run on GPU. And this is a recent project from Google called JAX, which is really just like NumPy, NumPy, matrix math, plus auto differentiation, and then compilation to code that can run on GPUs or TPUs. It doesn't have all the deep learning layers, and it's also not just for deep learning, but it's just a way to like do really fast numerical computing on GPUs, and it's been picking up a lot of steam. Then there's kind of task-specific frameworks like Hugging Face. So Hugging Face is on top of both PyTorch and TensorFlow, and they've written a lot of different model architectures, mostly for NLP, which is very valuable, right? So it's like, yeah, it's cool that we have a conv layer, but can we have a whole BERT model? Well, with Hugging Face, that's the level of abstraction that they're at. And they also share pre-trained weights for all these models, which is really useful. So distributed training, someone asked about, and it's a big topic. What that means is it's using multiple GPUs and potentially multiple machines to train a single model. So that's more complex than just using multiple GPUs to train multiple models, as in running different experiments. But it's really a must-do nowadays because the data sets are so big and the models are so large. It really just takes forever to crunch through the data on a single GPU. Versus if you do data parallel training, what you do is you split up essentially, let's say you want a batch size of 100 and you have 10 GPUs. You can distribute that batch such that each GPU gets 10 examples. They crunch through the computations, and then they do their backprop updates, and then they share what their gradients were with some central place, which is usually just the CPU or just one of the GPUs. And then the gradients are averaged and then pushed back out to all of the GPUs. And this is almost a linear speedup. So if you have 2 GPUs, you should expect like a 1.9 speedup. If you have 4 GPUs, a 3.5 speedup. This is borne out in benchmarks. So data parallelism is what people usually mean when they talk about distributed training. And it works well. We'll see in the next couple of slides how to implement it. Model parallel training is a different beast. And that's necessary when you can't even fit the weights of the model on a single GPU. So data parallel assumes that all of the weights of the model are on each GPU, and we're just splitting up the data to the GPUs. Model parallel means that we're splitting up the weights over GPUs. Okay, and that means the data has to go through all the GPUs. This introduces a lot of complexity, and if you can avoid it, you should try to avoid it. This is probably changing, like the frameworks are making it easier, and there's research coming out that makes it better. But for now, it's better to just buy the largest GPU that you can, or use the largest GPU in the cloud, and then use tricks like gradient checkpointing, where you don't necessarily have to hold all the gradients in memory at once. You can just write some out to disk and then kind of load them piece by piece. So if you want to do data parallel training in raw PyTorch, it's actually pretty easy. So here we say, model equals model, and then if torch.cuda.device count is greater than 1, then we're going to use several GPUs, and we say model equals nn.dataParallel of the model. So that does the secret sauce magic. That now lets PyTorch know that data to this model should flow to different GPUs. Then we move the model to device, except now it's actually multiple devices, just automagically. And then when we train, we will see that our batch size is 30, but inside of the GPU, there's only 15. So there's 2 GPUs, so it splits up that batch of 30 onto 2 GPUs so that each GPU gets 15. With PyTorch Lightning, it's even easier. You literally just say, dash GPUs equals whatever. If you have 8 GPUs equals 8. And then you also say, accelerator GDP, distributed data parallel, just so that it's fast. And it's actually also possible to use Slurm, where you also say dash nodes equals 4. And then you define the task to say, there's 4 nodes, 8 GPUs per node, and so on. Then there's specialized, software for distributing models over GPUs. Horovod from Uber. Yeah, so here it says, accelerated GDP, so distributed data parallel. That's a piece of PyTorch code that implements, syncing the weights, sending the data to the GPUs, keeping track of all that. So Horovod has its own system that you would use instead, and they use the standard MPI framework instead of like some specialized code like PyTorch distributed data parallel, or in TensorFlow, like TensorFlow distributed. So I mentioned Anyscale. So the project Ray, which is the original open source project, the vision of that project was not deep learning specific, but it was just to make stateful distributed computing really effortless in Python. So if you write your code and then you launch it through Ray, then Ray takes care of basically syncing state across distributed system. So it could be useful if you're not specifically doing deep learning, but you're just working in distributed computing. Let's talk about experiment management. So just running one experiment at a time, it's actually surprisingly easy to get lost into which code version and which hyperparameters and exactly what type of data, or which version of the data generated the trained model that you produce. And it gets a lot worse if you're running multiple experiments at once. So a low tech way to deal with this is a spreadsheet, and just, here's what I did. This is the data set, this is the git commit, these are the hyperparameters, these are the results. And that's what people used to do. With TensorBoard, it's better. It's automatically tracked. By the way, our labs with the PyTorch Lightning, you automatically get TensorBoard for all of your training runs. And that's a fine solution for single experiments. But as you run, dozens and eventually hundreds of experiments, it's just not a great interface for looking at everything you've done and being able to make sense of it. It's a good way to look at a single experiment, but not at many experiments. So there's software that makes that part of it better. So here's an open source project from Databricks called MLflow. And they do several things, but kind of the central thing is this experiment management platform where you get just a log of everything that happened and then a table that you can kind of filter on and stuff. Specifically for, to go further in that direction, there's startups like Comet or Neptune, which let you look at individual experiments, but then also have a table of all the experiments you've ever done that are searchable, have a chart where you can see the sensitivity of the different hyperparameters to the eventual accuracy. That's that chart on top there. Even like see the diff of the code at the time that you ran this experiment, you know, to the most recent commit, and then store the results, like the trained weights of the model. Weights and biases is another solution that enables all of this, and this is the one we're going to use in lab. It's quite nice, and yeah, tracks GPU utilization, all your runs in a table. I mean, you'll see it, so I won't spend too much time on it. And then another thing weights and biases lets you do is actually embed all of those charts and parameters and stuff into a nice report, which you can write and then share with the world or with your group or whoever else you want to share it with. So you can combine text and like machine learning artifacts in one document. So briefly, that's about experiment management. It's useful to have software that helps you decide what experiments to run and just to run them kind of for you. And that could be as simple as just being able to say, you know, on the command line, instead of saying, you know, learning rate equals 0.1, could we say learning rate equals between 0.0001 and 0.1 uniform distribution, and then have something just generate a lot of experiments and sample that space. And it'd be even better if it wasn't actually random, but if it was selected intelligently in some way. And also, like, as you're running experiments, some experiments are just clearly not going to be, like, they're not going to be as good as some experiments you've already run. You can see that from the beginning. Like, the loss is always on top of the loss of another experiment. It'd be cool if we could kill those runs early. SIGOPT is one company that that's their bread and butter. It's an API where you can tell them, you know, what parameters you're about to run. You know, you tell them what parameters you want to kind of search over. They'll tell you the values. Then you send them the output of the training, and then they tell you the new values, and they can tell that to like many experiments at once. And they suggest values in a way that's optimized. So they use the Bayesian optimization here. If you don't want to use an API, you can use your own, you know, local software. So Ray Tune, another project in the Ray ecosystem, can do this. So they have state-of-the-art algorithms like population-based training, hyperband, and basically, you know, they will give your training runs the resources that they believe are the most promising, or the hyperparameters that they believe are the most promising, and they'll also kill training runs that are clearly not going to be the best. Weights and biases has this feature also, and that's actually what we'll use in lab since we're already using it for experiment management. And so the way that works is you define here on the right, it's a YAML file that just that says, okay, use Bayesian optimization. I want to minimize validation character error rate. I want to terminate early using the hyperband protocol. And then I want to explore this parameter space of like different conv dimensions, window width, you know, fully connected dimension, whatever. And then it's called the sweep in their language. A sweep server is started on their machine in the cloud. And then on our local machine, we start agents. And the agents basically request a set of parameters from the server and then just execute. Everything's logged to WNB. And then you get to record all of your experiments and see how they perform. Lastly, all of these things, right, even including data and deployment and all the parts of training and evaluation we talked about, there's solutions that kind of try to do all of them. Usually that takes the form of a notebook server for development, being able to provision a lot of compute and launch a lot of experiments in the cloud, then tracking the results in some kind of weights and biases type table. Sometimes even deploying the model as a REST API endpoint or getting some artifact that you can deploy on edge. and even maybe monitoring the performance of the deployed model. The earliest that I can find of describing like this all-in-one machine learning system is probably FB Learner from 2016. So it was an article that described Facebook's AI backbone, which starts with data. There's a feature store that extracts features from the data, stores them somewhere. Then a training part, which also uses GPUs, which produces a model, which then gets deployed again on the CPU as an inference engine, and then is displayed to the users in a way that, as they interact with it, that feeds back into the data store, and the process repeats. Since then, the cloud vendors like Google, Microsoft, Amazon have come out with their all-in-one systems. The Google Cloud AI platform has, things for data labeling, BigQuery for basically warehousing data. They have AI platform notebook instances, which give you like a really easy to use notebook. Training, which you can use to spin up a lot of machines to do training. For validation, specific ways to look at the model that you've developed and try to get some visibility into it, and then a way to deploy it. Amazon SageMaker that's the name that the Amazon, basically machine learning system has. And once again, it has SageMaker Ground Truth for labeling, Data Wrangler, kind of like BigQuery, data processing. Then you have Studio Notebooks, which gives you an easy notebook. Then one-click training that gets you like provisioned hardware to do the experiments, keeps the results of the experiments in SageMaker experiments, deploys it, and even has some model monitoring. Neptune is a startup that tries to do the same. They kind of have that whole system also. So does Floyd, Jupyter Notebooks, deploy trained models. You get GPUs kind of at the click of a button. Gradient by Paperspace is another one. So once again, you got that 1, 2, 3, 4, develop, one-click Jupyter Notebooks, train, deploy, model serving, and then scale. Determined AI is an open source solution. Everything up until now has been a paid system. I think Paperspace Gradient has a free tier, but it's all public. So if you want private experiments, that you'll have to pay a little bit. Determined AI is open source. It's actually also from people originally from UC Berkeley. And they don't do the data or the model deployment steps, but within the model development and training, they try to cover everything, right? So from resource management to a really easy distributed training, to tracking experiments, to searching over hyperparameters. In fact, some of the founders of this company are I guess, most well known for the hyperband algorithm. So this is definitely worth a look, determined.ai. Among the startups, I think the one that comes closest to covering everything is Domino Data Lab. You can provision compute, you can track experiments, you can deploy the trained model as a REST API, you can monitor the predictions it makes, you can publish like Streamlit-like little applets for the, leads. They can monitor the spend of their data scientists. They can see all the projects and kind of their statuses in one place. It's not quite targeted at deep learning. It's more targeted at like just kind of more old school standard machine learning on structured data. But I think this is the type of feature set that a lot of these vendors are approaching. So I just wanted to show more of that. And really, it's a natural place to go for most machine learning operations companies. So for example, weights and biases, they got started in experiment tracking, giving you like the dashboard of experiment results. They expanded to hyperparameter optimization via sweeps. They also have dataset versioning called artifacts, right? They have reports. Apparently production monitoring is coming soon. So as we look at the ecosystem of all these vendors, I think a lot of them have the inclination and tendency to like push out into the surrounding areas. So breaking it down a little bit, we can look at weights and biases. They don't provision hardware for you, so that's not available. They don't manage resources for you, so they don't like allocate GPUs to your experiments, but they do help you do hyperparameter optimization. They will store the artifacts you produce. They'll help you review experiments, and they don't currently help you deploy or monitor. Paperspace Gradient uses Paperspace GPU hardware. They have their own cloud. They will help you do resource management. They will not help you do hyperparameter optimization, but they will help you do experiments. And I guess they do help you deploy, so I should fix that. And then you can kind of look at the different vendors on this in this table. The pricing of these vendors is something that often isn't totally clear, and it kind of depends on your team size and exactly how much you'll be using it. SageMaker instances tend to be, they definitely have a markup over the, like if you just use basic EC2 instances, that would probably be about 20% cheaper or 40% cheaper than using those same instances but provisioned via SageMaker. So there's a premium for the ease of use that SageMaker charges you for. Domino Data Lab is pretty expensive. Determine AI has an open source solution, so that might be worth starting within a research environment. And then some of these are free for personal use, like Weights and Biases is free for personal use, but your projects have to be public, which is not usually a big deal if your data sets are public. But if you're training on some personal information in your data sets, then you need, a private account. So someone asked, like, how do we stay up to date with this stuff? Like, how do you find all this? So one way that you can try to stay up to date is follow us on Twitter. And every Tuesday, which I guess is today, we do Tooling Tuesdays where we talk about some part of this ecosystem that is useful. And we explain why it's useful. And sometimes we explain like what other alternatives exist that you could be using instead of it. So that's a good way to do it. And then, yeah, I think Twitter is a really good way to kind of build a community and follow some people that tweet a lot about these subjects. We should probably at some point have a slide, maybe towards the end of the class, where we just have like a bunch of people to follow, suggestions to follow. So that's it for the lecture. I thank you. Just to make sure that there's no more questions.